Okay, good morning, folks. Absolutely delighted to be here today for our DSRT. We've got two guests today, and I'd love to take a moment to introduce them. We've got XY Han and Kirill Skobelev, who will be talking about what will get us to surgical AGI. Let me take a moment to introduce them both formally. Dr. XY Han is an assistant professor of operations management at the University of Chicago Booth School of Business. He holds a PhD in operations research and information engineering from Cornell University, an MS in statistics from Stanford University, and a BSE in operations research and financial engineering from Princeton University. His research focuses on uncovering the mathematical and operational foundations of modern artificial intelligence, using large-scale computational experiments and geometric analysis to better understand how AI systems learn and perform. Dr. Han has made several influential contributions to the field, including co-discovering the neural collapse phenomenon in deep neural network training and co-inventing the survey descent method for non-smooth optimization. His work has been recognized with the ICLR 2022 Outstanding Paper Award and as a finalist for the ICCOPT 2022 Best Paper Prize for Young Researchers. Through his research, he continues to advance the theoretical understanding of AI while developing tools that improve real-world performance across complex domains. I'd also like to take a moment to introduce Kirill Skobelev, who is a pre-doctoral researcher at the University of Chicago Booth School of Business's Center for Applied AI and also an incoming PhD student in computer science at Northwestern University. He holds a BA in economics from the New Economics School, and his research interests include AI and decision-making in long-horizon, sparse-reward domains such as medicine, business, policy, and law, interpretability methods that create a two-way supervision channel between humans, MAI, and meta-science. Guys, we're absolutely delighted that you're joining us here today. I'll pass it over to you to start the conversation.
Hey, thanks, Rachel. That was very kind. If I knew you were gonna read all of that, I would have sent you something shorter. Um, and yes, I appreciate your calling me Dr. XY Han, but like the doctor is in the like Ross Geller sense, not the real medical sense. Um, which is kind of oddball here, I guess. Anyway, so I'll start this off and then I'll hand it to Kirill, who kind of knows the nitty-gritty of the experiments better than I do because he ran them. And feel free to interrupt us at any time. We come from a school where that's very much the norm. So, right. So the question we're kind of working with the SDSC to solve, we're very much the AI side of things, which is what will get us to surgical AGI, and what does that even mean? And the reason that this is even a question is because of these scaling plots that if you kind of troll Twitter or like any news outlet, um, are appearing pretty frequently, which is people show these exponential growth curves where both the hardware that is available is growing pretty quickly, and also the capabilities of these models in terms of just how much they can do and how much power they consume is also growing pretty quickly. And it gives us this impression that we're very close to this idea of artificial general intelligence, which is basically maybe we can do away with the people behind all these decisions. And I guess in the SDSC's case, surgical decisions, and let the AI take the wheel in a large portion of that. And this is just the popular belief. And the in the medical domain in particular, if you're an outsider, like in some, I am, right? I work with you guys, but I'm still very much just the AI researcher. Um, this doesn't seem rhetorically to be so far um, out of the question. Like you see papers like this that kind of create these question and answer multiple choice benchmarks that ask like, oh, if you were in this situation, what would you do? It looks very much like a pencil and paper exam, and like a typical person reading these questions without medical training would not be able to answer these. But you see these LLMs answering these quite well because they kind of memorized every medical textbook out there. And there are people, mainly the foundation labs even, who like to push this narrative and especially push the narrative that we have more compute, so we will be able to accomplish this faster than anybody else. And the incentive here um, is that if you're, say, the SDSC or if you're a hospital, then you'll be incentivized to work with these big players, whether it's Microsoft, Anthropic, NVIDIA. Give them your data, they'll lend you their compute and look at what compute can do. It's like on this question and answer pencil and paper meant QA benchmark, they're getting close to 100%. So they like to make you think, at least, that we're very close to creating these AI doctors. Um, if only you give them your data and they lend you their compute. And again, like it's very much in their interest because these are companies that need to grow. These are pre-IPO companies. These are companies that really require the buy-in of the public and the data providers to keep succeeding and growing as they are. And as such, like whether you believe them or not, the kind of industry leaders go on to these interviews and they say things like, "We're now confident we know how to build AGI as we have traditionally understood it. On the Anthropic side, we AI-enabled biology and medicine will allow us to progress the progress of human biologists would have achieved over the next 50 to 100 years in the next 5 to 10 years." Um, when reading things like this, yes, like it's inspiring if you're just out of college or 20 something years old, you think, "Oh, I need to work on this. This is the future." Um, but you have to remember there's a lot of interests behind these words, which is they want these 20-year-olds to work with them and they want these hospitals and nonprofits and data collectors in general to work with them because without this data, they can't do anything. And right now, like computing costs far outweigh the actual profit generated by AI. It's more of an industry running on investments right now than actual produced profit. So basically, it is very much to their interest if you were to believe this. Um, but then again, like I appreciate the AI generated photo here, but it does create this vision in your mind that they want you to think, which is, oh, like can we just sit back and enjoy the benefits of AGI? For those who are kind of new to this culture, AGI just means like the robot has taken over. It can kind of act as an autonomous and very intelligent being, and it will do your jobs for you so that we can work in what someone in Anthropic once told me in a post-work society. What that means is kind of if you imagine the movie Dolly, right? Like the people kind of just sit back, eat, and sit on their floating couches, and the AIs do all the work. So like quotes like this makes it seem like, oh, really, like we're not that far off. It's like not just within our lifetime, but within like the foreseeable future. So then we can look at it at a bit more granularity. And again, like there's a lot of companies and a lot of research teams pushing this narrative, which is, hey, like we created this medical benchmark in this and whatnot way, and we did so well on it, and we're only doing better. clearly that means we're almost there. But something that was actually brought up by Dan a bit after we released the initial version of the preprint we're going to talk about soon is if you look at this table, and generally if you kind of just scroll the web for these medical AI tables, none of them actually contain any surgical benchmarks. And after Dan brought this up in an email, I kind of had Kirill look into it. And like it's pretty consistent. Nothing like it's basically like fMRI images, X-rays mostly, like multiple choice exams. But really, like surgery is very, if you're looking for it, very saliently and clearly omitted, which puts you guys as in the SDSC, in a very interesting position because you seem to have ended up in this very specific corner case and bottleneck situation where the one thing that's like not solvable naively by AI is exactly what you do. And like again, we looked on the WHO, and according to the WHO, right, surgery, there's around 313 million surgeries per year worldwide. Um, Probably there's caveats to that, but let's just take the WHO at their word. Almost all of it now is recorded. As you know very well on your end, almost none of it is labeled unless you guys do it yourselves. But this does seem like a nice body of data to look into because AI is trained with data. And if this data is out there, even without labels, does this mean that eventually surgery will be kind of taken over by AI? And how far are we from that? Which kind of inspires the title of How Far Are We from Surgical AGI? Don't freak out. This is very much we checked the code. This was one of Dan's surgeries, so I think we're pretty safe here. It's pretty de-identified. But these are the type. This is just an example of the types of videos um, that AI is working with, and like you guys know this much better than us. But you see things like suction and it will let you like identify where the tools are. But this is kind of a first order task, which is like before we even talk about, let's say, can AI do surgery? The question is, can AI even process the signals that would tell you what's happening in the surgery? And if it can't even do this, everything else downstream is off the table. And that's kind of the premise that we're going to start with for our experiments, which is can it even do tool detection? Um, and with that, we're going to jump into the experiments and I'll hand it over to Kirill.
Yes, awesome. Thank you, XY. Thank you, Rachel, for the introduction, and thank you, everyone, for tuning in. Let me just quickly walk you through what we're going to talk about in my section of the talk. I'm going to introduce you to the models that we use in the paper. I'm going to show you some benchmarks, some data that we use as benchmarks. We're going to talk about methods, so what we did to those models and to the data to get the results that we got. And then we're going to discuss the implications of our findings. So in the paper, we worked with mainly two types of models, vision language models. The most common example would be a regular chatbot like ChatGPT or Claude or Gemini. That would be a closed weight VLM. So we could only use it as a black box. We have the input, we have the output. We don't really see anything that's happening inside the model. There are also open source VLMs like Gwen or Gemma, or should I even say open weight VLMs. The benefit of using them is that we can change the weight so we can fine tune the model. And then we also, the second type of models that we looked at were computer vision models. And a good example would be YOLO or SNet. Just a quick note on how VLMs work. Basically what happens in the transformer is you have a sequence of text that is represented as numbers, as vectors, and then it's passed through the model. What happens in a vision language model, there is a separate encoder that takes the image. It makes a smaller vector that represents that image called an embedding, and then it just attaches that vector, it concatenates it with a text vector, and it passes it through the model. So in some way, the model treats images the same way as it does text. And sort of the quick recap of how computer vision models work. A regular convolutional neural network would be a good example. So it takes the full image and then it passes it through the layers of the network. And then we arrive at this smaller vector at the end of it, which is usually something like a vector of logits or activations. And it's also relevant to mention YOLO and bounding box detection. So the models like YOLO split the image into a grid, and then for each small square in the image, they give you a probability of a certain object being in that box. Let's take a step back and think of the task that we have at hand here. So we want to identify tools from surgical frames. And sort of on the left, you're going to have generalist VLMs. And the way we would work with them is we would give them the image, we would give them the prompt, and then we would instruct them to give us some kind of machine-readable dictionary as an output. And it'd be in a chatbot kind of format. And then on the right, we're going to have small specialized models. We're going to have YOLO, ResNet, and that would work as traditional machine learning. You would pass the model through the neural network and get those class probabilities at the end. The datasets that we worked with, the first one, the main one, the paper is SDSC's new dataset, SDSC's EEA, which is quite a mouthful for someone who doesn't have medical training, but it is endoscopic, endonasal approach pituitary tumor removal surgery. We also check robustness of our findings on two datasets. The first one is Cholic T50, which is a colectostomy dataset, and also in PitVis 2023, which is also a dataset of pituitary tumor surgeries, the same way as DSC's dataset is. And here's a quick comparison. So I guess the main takeaway from this table would be that these datasets are quite large. There's almost 70,000 frames in SDSC's dataset, and then Cholic and PitVis have 100,000 frames. And then the complexity of the task of tool detection differs by the dataset. So Cholic T50, for example, only has 6 tool classes, whereas SDSC's dataset has 31 classes. So it kind of becomes a more sparse problem. And then we perform our own train validation split, where we keep procedures in separate sets. So the metric that we're going to use to evaluate model performance is very straightforward. We are just going to see if the set of tools predicted by the model is the same as the ground truth. And then we're just going to take the average of that over a sample. So if it's correct, it's 1. If it's not correct, it's 0. And that would give us exact match accuracy or exact match rate. And with VLMs, the final note before we jump into results, it's useful to know that we have 2 modalities of working with the VLMs. There is zero-shot evaluation. So we just give the model the prompt, we give it the image, and then we grade the results. And this simulates sort of what a chatbot user would do. They wouldn't do any training of the model. And there's also LoRa fine-tuning, which is basically additional training of that model, which we can only do for open weight VLMs because we have access to their weights. And this specific method uses this trick where we can modify a subset of the weights, if you wish, to save on computational costs. So this has to be my favorite plot from the paper. and we're actually going to focus on this lower right corner. Here we see the plot of exact match accuracy, so like our performance metric as a function of the number of parameters. And note that the x-axis is a log scale. So actually, there's quite a lot of variation in here. We tested models kind of ranging from 20 million parameters over here, but we're going to talk about the stars we can see in the sky here a little bit later. And the VLM starting from 4 billion parameters and then going all the way to the 100 billion. And so there are a few things that we can notice on this plot, right, and sort of motivates our further experiments. The first thing is that, first of all, like most models fall below this black dashed line, which represents the majority class baseline, which is simply we take the training data set, we take the most common predicted set of tools, and then we use it as a prediction on our entire validation data set. And in this particular case, and I think in colectostomy, it is actually suction. So suction is the most common set of tools present in the frame. And no model. So we benchmark different model families. And so within, for example, Quen family, we took different generations. So we took Quen 2, we took Quen 2.5, and we took Quen 3. They are, you have this like historical perspective here also. And we can see that they really fail at this task. So they do worse than chance. Except for this one model, which is Quen with 200 billion parameters. It looks like it slightly jumps over majority class baseline, but it's still nowhere near what is possible. And we know what is possible using those kind of stars here. And then the second thing to notice in this plot is that, yes, it does seem like there is some kind of linear positive relationship between parameters, model size, and exact match accuracy. But it is highly model family dependent. And then if we look at the shape of the curve that dependency creates, it looks like it's very sublinear. So it means that, if we grow, and again, this is a range from 4 billion to 200 billion, we'd have to grow the models beyond the point that is actually possible with current hardware, or the hardware that would be possible in the next 5 to 10 years.
Kirill, can you go back real quick? Let me put two little comments there. So two things that so Kirill did a really good job with this plot. So one thing is like that black dashed line. Like he kind of brought this up, but I really want to emphasize that's the dumb I know nothing. I'm just always gonna choose C on the exam answer because I know like C is the right answer more than others. Like that's what you would get if you just pick C all the time, right? So a lot of these models, we say they're getting better, but actually they're getting better to the point where they're barely getting to the point where you would if you just do the dumb I don't know the answer strategy. And the other thing is the fact that Kirill pointed out, which is as these models get bigger, you are seeing an improvement. That's actually what the general public calls its scaling laws, which is as you push more of the generic internet into these models, people believe, oh, like eventually if you scroll the internet enough, you'll know so much that your knowledge will generalize. That does not seem to be the case here. Like they're pushing more and more of the internet into these models, and they aren't even beating that 18%, 13% random guess baseline. The other two things, like again, Carol already pointed out, which is the two stars in the sky. Fine-tuned means we use the SDSC's data, we split it into a training and test set so that like you're not like testing on what you train on. that data actually caused a significant improvement in the model quality. So this will be a recurring theme going on, which is it's about the data, not the models in some sense. Like the data on a much, much smaller model actually got the best result in this square here. That's the first thing to notice. That which relative to the SDSC, right? Like it means that you guys actually hold a very significant point of leverage in this space, which is the foundation labs can push as much generic data into their models as they want, but they can't do that much without this specialized data, which is like protected by US laws and protected by all the contracts and trust that the SDSC has built. So it's the first point that will appear multiple times in the future in these slides, which is the data is going to matter a lot more. And the final thing I'll point out before I hand it back to Kirill is notice that the y-axis, like even with the like really cool like gold star on the top left, which is way above the random guess line, that's only like 50 something percent, right? This thing was labeled by human professionals. So a person is 100%. Like we know this, like by construction of this data set, a person does 100. So the thing to notice is we're nowhere even as good as just the regular professionals that you hired to label this data. We can get close and we can get way better than chance, which is not something we could do 10 years ago. But we're nowhere close to something like an autonomous AI. And this might actually be why surgery has generally been excluded from all those hype farming medical benchmarks that you see on Twitter every other week. Um, right. So I just wanted to point these things out, and I'll hand it back to Kirill.
Yeah, thank you, XY. So can you see the laser pointer here?
Yes.
Yeah,
Yes.
yeah, okay. Awesome. So yeah, this is a new feature I discovered. So another interesting point with this plot is that so yeah, as XY said, you know that those frontier AI labs talk about how their models are like really good at medicine. And then here we can look actually, this is one example. We have Gemma 3 and we have Med Gemma 3. So those points are those two models. And so like Med Gemma 3 is Gemma 3's medical uh, sister. And they have the same number of parameters. But then on the plot, you can see it's kind of cluttered in here, but if you zoom in, um, that the performance of the medical model is actually lower than the performance of the original. It's not significant, but we can see is that, yeah, so models that are claimed to be good at medicine, they really, it's entirely possible that they're only good at those text Q&A benchmarks, or at least the stuff that um, the labs were able to train the model on. So yeah, another perspective on this data. So we have exact match accuracy on the y-axis, and it's a little bit more, it's more limited because we're not looking at those fine-tuned models that we have here. That would be meaningless. But here on the axis, we have MMBench, which is one of the most commonly used benchmarks, visual that they use to benchmark visual language models. Another one you might have heard about when a new model comes out, there is a release. Benchmark is called MMOU, and in those benchmarks are kind of meant as a gauge of how good the models are in terms of their general visual intelligence. And the kinds of questions you would see, there would be something like they show a picture with some fruits, and then the model has to tell you how many apples it can see in the image. There are some more complex questions, but that's the general idea. And what we can see is, yes, there seems to be, again, a positive relationship between the general purpose benchmark and our surgical benchmark. But then even if we were to saturate bench here, and if we were to get a model that scores 100, which is the highest score in the benchmark, sort of doing this very back of the envelope extrapolation, we don't get the meaningfully high level of performance on the surgical benchmark. What that tells you is, like, if you're given two models and then you know their general benchmark scores, you know their MMOU scores, bench scores, you can probably tell that a model that has a higher performance on this benchmark will do better in the surgical task. But without evaluating the model on the specific task, you would not be able to know what the level of performance is. And here we can see again, it is below always choosing C in XY example. So the next natural question is, can we train those models to do better? And that's where LoRa fine-tuning comes into play. And this is what we did. So we took Gemma 3 and then we trained it using the train split of SDSC's dataset. And here are the loss curves. Here are the exact match accuracy rates. And what you can notice right away is that the validation accuracy improves, but then the improvements taper off, and you kind of see this. It looks like there is a ceiling to what it can learn, and this can be explained really by two core reasons. The first reason would be insufficient model capacity. So we can see that there is this gap in the train and the validation set, and you could say that maybe this gap is due the model being too small, and maybe it's overfitting on the train set, and then fails to extrapolate it to the validation set. And then the second reason would be that the data is just not sufficient. So even if we have this massive data set with 70,000 frames, that is not enough to learn the relationship with the model. So we have two hypotheses here, and we are going to argue that it is the data, and then our further experiments are motivated by this question. So we are going to rule out that the reason why we see this train validation gap is model size. So yeah, going back to this plot, this red box is showing you the fine-tuned Gemma model. So it's way above all the other VLMs at the same number of parameters. So yeah, it is useful to know that it is definitely possible. It is definitely possible to get better performance out of the existing models with the specialized data that SDSC has. And then, so going back to this question of whether this train validation gap can be explained by model size, there really it kind of splits into two different sub-questions. And the first one would be, well, maybe maybe our adaptation is limited. So maybe the number of parameters that we're changing in this LoRa fine-tuning. And remember that, LoRa fine-tuning, we don't change all of the model parameters. We change only a small subset of them. So maybe, a LoRa rank is too low, and maybe we're not changing enough parameters. We tested this, and then we did a LoRa rank sweep going from 2 to 1,000. And what this means is it's shown in this table. So we changed the number of trainable parameters from about 5 million to 2.4 billion. Oh, it's a massive range. The first thing to notice here, and then we report train accuracy and validation accuracy on this plot. The first thing to note here is the gap between them doesn't really go away. So as training accuracy saturates, and again, so 2.4 billion is massive. It's a massive adaptation happening. The validation accuracy is still 50, 60 percentage points below train accuracy. What this tells us is that probably LoRa adapter capacity is not what is limiting us from getting getting to this performance that we wish was there. And the second thing to notice here is that, again, this dashed line here is the majority class baseline. And it takes us sort of going to 128 to jump over that. And a lower rank of 128 means that we trained basically a 300 million parameter model on top of it, which is, again, a lot of parameters. So if we're gonna look at the specialized computer vision models a bit later, and so the largest one that we experimented with was only I think 27 million parameters. It was under 30 million. So so this also shows you that using VLMs and training VLMs for those kinds of tasks is just very computationally inefficient. So training, we had to run this on a GPU cluster. It's not something you could do at home on your laptop necessarily. So yeah, so the second sub question that we have about model size is that, like, what if our Gemma model has 30 billion parameters? What if that model size is our bottleneck? What if we need this GPT-8 model with a quadrillion parameters to learn surgery? And what we do is we take this specialized model called YOLO V12. It only has about 30 million parameters, and it's much better in terms of cost of training and in terms of cost of inference than all the VLMs. And it actually performs slightly better than the fine-tuned Gemma model. So what this tells us is that underlying model size isn't really the bottleneck, because we can achieve similar results with 1,000 times less parameters.
Let me jump in here real
Yeah.
quick. So the what's kind of underlying what Kirill has said for the past few minutes is that there's this general belief out there that something like YOLO is basically trained to do one thing. It's trained to, in particular in this case, identify what tools are in the frame of the video right now. These other things on the right, they are, for better or worse, they're architectures that has had the whole internet pushed through them. And there's this belief now that's getting increasingly popular, which is this idea of cross-domain generalization, which is because you've read so much of the internet, because you've trained on these medical textbooks, at some point that knowledge will help you learn if you were just readapted to do, say, surgery, right? So the other knowledge is going to help you with the specialized knowledge more than if you were to just train kind of myopically on only doing that one task. And this belief for like AGI is almost here is built on this idea that because we've swept so much of the internet into these huge models, we can do this, and these huge models will eventually generalize beyond any specialized training. The whole point of the past few slides is we threw the kitchen sink at it. Like, we tried training these things to make them bigger and bigger. We threw like an ungodly amount of academic GPUs onto this task, right? And we couldn't get anywhere. Well, we got somewhat close to that YOLO, but we didn't even do better, right? So that story of the internet will set you free from the chains of specialization is not, as far as we can tell, true. Yeah, just to point that out. Kirill, take it back over.
Yeah, that's a great point. I think it kind of encapsulates what this paper is about. And so we have seen this using SDSC's new dataset. And now we wanted to validate those findings. What if we did this on this data set, and then maybe There's something special about SDSC's data that doesn't translate to other surgical domains. It turns out the answer is no. Like we see the same pattern, exact same pattern on all of the other benchmarks that we tested. So we tested Cholic T50, BitVis. We're
Wait,
currently adding
Kirill,
another.
your slide might have frozen. We're still on the. Oh,
No,
now we're.
yeah, okay.
Oh.
So yeah, I switched to the next one. So there's this other data set that we are currently benchmarking, and we're going to have it in the final version of the paper called Surge View. And preliminary results show that we have the same patterns in those three data sets. But we're gonna talk about Cholic and we're gonna talk about BitVis here. So we're not going to go through all of the plots that we have for those data sets. We're sort of going to highlight the main results in the summary table. And here, the majority class baseline, this is what would have been the dashed line, is 34%. The nice thing the nice thing about those data sets was that we could pass them through public VLMs because they are public data sets. So this is what you're going to notice that we have frontier closed weight models here. We have Gemini, Claude, and GPT. And another caveat with this data is that, of course, we don't know if those models were trained on it because they're kind of behind, not a paywall, but you have to fill out a form to get them, at least Cholic. But basically, we cannot about the models have seen the data set. Anyway, so you can see that GPT-5 and Claude Sonnet 4.6 are below this majority class baseline, together with Gemma 3. And Gemma 3 actually performs really badly on this data set. It's 6.8%. And then when we train it, actually raises up the ranks and becomes the first model here at 83%. Then we have Gemini and Claude Opus that do well. They do above majority class baseline, and with those data sets, that's what we're going to see with BitVis also. So they would have been on this plot. There would have been somewhere here. You can think of it, but still, still YOLO, specialized YOLO, and then Gemma that we train on this data does much better than those closed weight models. And another note is like we don't really know how many parameters those models have because it's not something that they release publicly, but there's some estimates, and it is very possible that the total number of parameters in those models is already in the trillions. We do the same LoRa sweep, and we find a very similar result. Here on Cholic T50, this gap between train and validation actually becomes larger as we increase LoRa rank in terms of percentage points. And again, it saturates, this performance saturates kind of around 80, maybe 95%. Sort of further training, again, this is 2.4 billion parameters that we trained here. It doesn't get us to closing this gap. And so a similar result for BitVis. The majority class baseline is 39%. And again, Gemma performs below that majority class baseline. GPT-5, Claude, and Gemini do better. So this data set would probably be in common crawl because BitVis is it's just like posted on the website. So those models, it's very likely that they've been trained on this. But again, YOLO, specialized YOLO, and Gemma that we trained still do better. And then again, this is somewhat an incomplete LoRa sweep, but then it still goes from 4 to 1,000. We can again see this distribution gap between the train and validation, and kind of saturation of training accuracy but validation accuracy not catching up to it. So these are the results. So we can pretty confidently rule out that model capacity, either LoRa fine-tuning capacity or underlying model capacity, is not something that prevents us from getting the surgical performance, and it is data. And it is something that, philosophers, economists, Michael Polanyi was this polymath in the early 20th century, something that economists have thought about for a while, this idea of tacit knowledge. He's the person who coined it. And the idea of tacit knowledge is that there's something that people learn that is not explicit. So it's not something you can read in the textbook. It's not something someone can tell you in words, but it's something you have to learn at the job. And this is, something the medical profession is known for a long time. And that's why, if I'm not wrong, I think in medical training, you take 2 years of classes and then you do 5 years of residency. So you have a larger chunk of your educational time that is spent actually getting your hands dirty. This is something business schools have also known. A lot of MBA classes are based on cases, so they kind of role play making decisions in the real world. And this is, again, something that shows up with vision language models. So you can ask Gemma all sorts of questions about, for example, endoscopic intranasal surgery, and you're going to get those answers that look fully professional, and they are mostly correct. So that we know that it has memorized the textbook, and it can pass those sort of Q&A type of exams. And this is something we've seen with the medical text benchmarks. But that does not mean, so again, coming back to tacit knowledge, does not mean it's going to do well at this specific surgical task. And it's not really about it being a visual task. It is about data availability. And this is something we wanted to highlight with this nice slide with ones and zeros. So it's data, data, data. And then this is why the world needs organizations like SDSC to pull it all together and train, train models or have this intelligence develop. And the final point that we make in the paper is kind of it's interesting to think about this trade-off between using generalist VLMs and specialized models. YOLO and ResNet that did super well on those benchmarks. They can be, you wouldn't want to do it in your laptop because they're just overheat, but it's something you could in principle train on your laptop and definitely run your laptop, right? So, but if you're using generalist VLMs, you are relying on this infrastructure, you're relying on the GPUs, you are relying using a lot of energy. Let's say if you're running it in the hospital, right? If you're using an external provider, their servers can go down. If you're using your own servers, your GPUs can become idle. They can break, and that would like put a barrier towards care. And if instead you have something that runs in your laptop, really it's more of a decentralized, I wouldn't say democratized data processing method, right? So I think we can finish the presentation and then we can jump into the discussion.
Great stuff. Thank you very much. Okay, let's see if there are any questions. So, folks, just raise your hand or just hop straight into the conversation. Okay, looks like you've stunned the audience into silence, guys. Um, oh, thank you, Jack. Jack, there you go. Over to you.
We have a planning question here.
It was a great presentation and yeah, just like congratulations on all the work. I had a question about the your opinion on kind of domain shift versus task shift, and whether you see or feel there's any difference between using because I guess YOLO is designed for object detection, whereas the other models are kind of more general. So there's like a shift in what they've been trained on, but also in what they're trained to do, the way they're built. And I wondered if you had an opinion there, and then whether maybe the YOLO models or some of the other models being pre-trained on like Cocoa, those kinds of things, whether that also makes a difference in terms of the amount of object detection they've done before we get to our downstream task.
Maybe I'll take
Um,
this one. Or
yeah.
Kirill, go ahead.
Oh no, go ahead. It's fine.
The answer is of course, right? Like the YOLO is meant to do something very specific, while VLMs are meant to just kind of answer your generic questions about pictures. The question here is so basically everything you said, Jack, is correct, which is like YOLO was pre-trained on in a different way. It's meant to do a very different task than what the VLMs are meant to do. So in some sense, that's the point. And the other thing is, what is this paper? What is this paper really kind of rebelling against? This paper is rebelling against the idea that just because we have ChatGPT, just because we have Claude, and these things, these generalist models are getting better, that we don't need specialized models anymore, or maybe the generalist models will eventually subsume the specialized models. Um, this paper is kind of meant to, within what computing capacity that we have, um, test that hypothesis. And the findings are not promising, right? So when you see these foundation labs on Twitter and on the internet saying, "Oh, great, like we're gonna work with blah 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 and just completely like take over the medical field and like the future of innovation is us," right? That does not seem to be the case. Um, it very much requires this specialized effort and the collection of specialized data before anything of that nature could happen. And it's not just gonna happen from VLMs, which as many people do believe. That's kind of how I would reconcile the two perspectives, which is everything Jack said is correct. And in fact, it's so correct that the internet itself is actually wrong on this. Right.
So stupid question.
Wait, I can't see who's speaking.
Sorry, it's me. It's the end. Hi.
Hi.
Yeah, stupid question. What is ChatGPT?
Oh, that's
Right?
interesting.
Like underneath it, like do you know what I mean? Like underneath the like, okay, here's some turns in a text game, right? Like what is the underlying model at this stage, 5.4, 5.5? Like we know, maybe think that there's probably a lot of different things ensembled, mixtured, routed, and so on. Is this if we're going to diagnose this as a small versus big, sort of presumes that what you see in the large open weight model is actually sort of the same thing as you see in the closed model, which I shouldn't even call it closed weight. It's just closed. Like they could be sending all of their things to my dog, and if he barks, then they provide this text output. And if he wags his tail, then it's this text output. It may be a little silly example, but I'm wondering how we reckon with this paradox of increasingly these most powerful closed models are so opaque that, like, do they just route all their things to YOLO, right? And it's just like, they haven't pre-trained a specific surgical video YOLO image detection model, but like they have for cats or faces or eyes or whatever. How do we reconcile this problem?
Okay, so I'm gonna so basically we Dan's right that we don't really know how modular that system is. So you kind of have to bet on the mentality of these masses. And you kind of have to look around the periphery to see what's happening. So relative to these models, I think there's been enough turnover between the foundation labs and the open source labs that we know architecturally, like there's been like computational savings in the language model architecture itself, but it hasn't really evolved that much um, relative to what we think like a transformer looks like and what the actual GPT transformer looks like under the hood with respect to like it's just a bunch of transformer layers with a lot of parameters stacked together. Now, relative to is it really offloading things to these like specialized cat detectors or something like that? It could, but it would not be the wisest thing to do. Um, and we can get that at that through multiple things on the side. For example, like we see these tool calling um, capabilities popping up in your ChatGPT subscriptions now. And you'll notice that as soon as you include a tool, it actually kind of slows down a little bit. And there's a reason for that, which is as soon as you start incorporating tool calling, you have to start scheduling things between the model. You have to pass things back and forth. Um, and it's nowhere near efficient. So for the models to have the latency that they do, that we observe for them to do, I don't think it's um, possible for them to have that many modular tools underneath. They probably have something to tell like the model how hard to think. They have something for content moderation. But I highly doubt that they actually have like it have like a collection of models doing this work. You might have seen the words mixture of experts, but that's actually not like we mix multiple models. That's within the same architecture, they have architectural branches. Um, the second thing I'll bring up is there's this shadow industry right now of data labelers, which is very confusing by design because they are basically these Russian nesting doll companies where like you have something like Scale.ai and you'll look at Scale.ai and you feel like you hear something about the fact that they're labeling data, but you never see what data they're labeling and you never see what they're doing. And that's because Scale.ai itself is not actually labeling the data most of the time. They hire a bunch of smaller companies that are subsidiaries, and anytime a job comes in to label data, they offload and subcontract these data labeling tasks to these subsidiaries. And this is important because legally speaking and reporting wise, they then create this veil of obscurity as to which foundation lab hired them to label what. And from anecdotal knowledge, what we do know is that all of the foundation labs, Anthropic, GPT, Gemini, they're all hiring labelers at scale. Like if you checked your LinkedIn, I'm sure like somebody in this chat has had a recruiter reach out to them saying like, we have this data labeling job. Would you like to work for us for like $20 an hour, just labeling data according to your expertise? And my guess would be that's actually what's driving a lot of this improvement, which is not only is it like computing scaling, but also the fact that these companies are identifying where their models are weak and hiring data labelers from things like Scale.ai to improve those specific points. For example, I know for a fact Gemini and Anthropic are hiring a lot of former Google software engineers to annotate and improve code. Um, so that's a very long and roundabout answer to say I don't think the improvements in these closed models are from architectural improvements. I think they're from very targeted data acquisition efforts by the foundation labs themselves.
Okay, explain, Kirill. Thank you so much for this DSRT. We're actually at time. So thank you for this conversation. This ends this part of the discussion.